Hey everybody, it's Tom Cherry Holmes with the FujiNet project, and I wanted to do a small little side video for the atom here, showing how I am patching Figforth to add atom-specific features and to get it ready for an atom-specific version. This video is going to be short because it's essentially going to cover a quick little tour of using the ed line editor and how I'm going to use it to patch one particular feature in the 8080 Figforth, and that has to do with how the 8080 Figforth outputs its text using the CPM output routines, which currently do not strip out the high bit. And you'll see why we need to do that in just a moment. In the next series of videos that I'm preparing for this particular subject, I'm actually going to go through the process of going through and patching Figforth so that it runs as an EOS application, using CPM as the development environment. And when it's ready, to assemble it and to write and assemble tools that will output the resulting binary image into a bootable form that will boot onto tape. But I digress, so let's get on with it. Currently, I have booted a version of CPM put together by William Hicks, which essentially sets up an 8 megabyte volume on drive A, which is very handy for software development. As an aside, when you were doing software development on CPM, you really wanted 8-inch drives, because at the minimum you got 256 kilobytes of space. You could double that to double density to 500K, and if you used both sides of the disk, that gave you 1 megabyte of usable space, which was excellent for source code development, for reasons that we'll see in just a moment. If we do a directory on this particular volume, I have everything I need in order to patch and do this particular feature patch. We have a complete CPM installation here with all the usual suspects, including the ed editor, which we will use. We also have Figforth in assembler format, and we have a pre-compiled version right here. What are we going to change? Well, we need to change how the console output routines work so that they will properly not emit the upper 8-bit characters, for reasons that you'll see in just a moment. If we take and run it here, you'll see that when we get into the Figforth environment, let's just do a vocabulary list. This is all we need to do to show this. If you see, you'll see the last character of each word here. These are all the words that are currently inside of the fourth environment that have been defined. These were defined as part of the installation manual. And as we go on to take and build this fourth, we're going to add more words to add things like an editor and an assembler so that we can have a fairly complete environment. But you'll see that each of the letters basically has the last letter in reverse or inverse video. This is because Figforth uses a technique known as last high bit to indicate the end of an entry in a table. It's very easy to detect in assembler, and it makes for some very efficient code when used properly. However, this high bit character is being displayed here, and it's having some unintended consequences. You can see part of the Atom logo in the middle of the screen because that character is being shifted up into the upper character set, which contains a piece of the logo. We have to fix this. We can type by to get out of here, and we'll come back to the prompt. And if we look again, we can see, just to kind of give you an idea of what we're working with here, I'll give you a quick little run through of ed. We'll just make a simple little text file with ed. you have to specify a file name. And once you do, you wind up in the ed environment with new file. Now you'll notice that the prompt is over here in the middle of the screen, and that's because the first 5 characters on the left-hand side of the screen are actually a line counter. Currently, there's no line or anything in memory here, so that is basically blank. And since there's nothing in memory, we can just insert the lines for the things we want to type in. How much memory do we have to work with? Well, if we send a 0v here, we can see that we have approximately 32K, a little more than 32K of memory to work with. So with that, we can hit I to insert and start typing in text. Typing characters as we need to, and so on. And when we're done, we can hit Control-Z to get back to the prompt, and we can save the file for editing. This takes the file that's in memory, writes it back out to disk. And this is important because ed uses temporary files to hold the blocks that are in memory before they are actually flushed out to disk. So you must make sure that you have plenty of space on your disk to not only hold your source material, but also your intermediate files and your output. This was actually why it was very common practice to keep your edited source code on a different drive. So with that, we take a look. We see our foo files. And it created 2 of them. It created the text file, but it also helpfully created a backup file for obvious reasons. So you can always take and use pip to take and restore a file by copying foo back over to foo text. But since this was the first iteration of the file, they're practically the same at this point. So with that, we can look at the file. Line 1, line 2, line 3, line 4. And we can bring it back into the editor here by opening it. Now you'll notice that we're back at this prompt here, but nothing is here. There's absolutely nothing in memory because we haven't told it to load anything into memory. Cursor is sitting up here at the top. We need to take and append the text that's in foo text into the memory buffer. There are 2 ways we can do this. The safest way is to give a number of lines that we know we want to append. If we use the number 0, that is a shortcut to indicate that we want to use no more than half of the available memory, which if you recall when we ran the v command before, that was roughly 32K, so no more than 16K of our available memory to hold our text. If we do that, we see that our cursor immediately jumps to line 1. And if we hit the return key, we can see the different lines start to come in. And in fact, if we take and start from line 1, and we type 10 lines, no more than 10 lines, we see our text file here. We can, for example, go to line 2, we can insert at this point. And we're back into the line edit mode. There's line 3, line 4. And now, if we take and do a type out, we'll see that line 2A was inserted on top of line 2. This is how the behavior of the insert command, and it's a good thing to keep in mind. So this was just kind of a quick little run through of doing basic edits and things inside of ed. I'm going to go ahead and kill this line here. We'll take and I don't want this line anymore. I'll kill it. And if we now go back and take a look, we'll see that that line is now gone. So, okay, we spent 5 minutes basically going through just kind of a real quick run through of how Ed works as an editor. We'll save the result here by pressing E to leave. And within a few moments, we'll find ourselves back at the CPM prompt. So now with that, we'll start in earnest with doing the modifications that we know we need to make. I'll go ahead and delete the foo text files. We don't need them anymore. And to let you know the size of things that we are working with here, let's take a look at Figforth. All of the Figforth files that we have using the stat command. We really don't need the number of records. What interests us here is the number of bytes that take up each file here. You'll see that Figforth, the source code, which is the ASM file, is 128K in size, which is roughly about twice as big as the total amount of memory that's in this machine. We also see the final Figforth COM, which is 32K in size, and we see the intermediate hex dump at roughly half of the source code. As an aside, for those of you who are not used to ancient development systems like this, you may be wondering why there's a hex file, why the assembler would be generating this intermediate file that you have to take and pass through a loader. And the big reason was, especially in the terms, in the context of CPM, CPM was originally developed to run on an Intel development system, the MDS 800. And the monitor ROM that ran on the MDS 800, the BIOS that you can think of when you first turn the machine on and it takes control, had a facility that could accept strings of formatted characters in hexadecimal to put a binary, such as something output from an assembler, into memory. And because this was text, it could easily be transmitted either over 7-bit lines, such as over a modem, or encoded, or more importantly, especially contemporaneously with the time, encoded onto 7-bit paper tape. This was very important. So it gave a way to easily take a portable way to encode a file that could be transmitted over non-binary friendly lines. So in a way, for those of you who are a bit newer, you can think of it as a form of bin hex, or you encode, decode, things like that. But I digress again. Apologies. So with that, you'll notice that I said before that figforth.asm is huge. It's very huge. It's 128K in size. And thus, it has a bit of a problem fitting into most word processors, full screen word processors and the like, that don't have some sort of mechanism for paging out to disk. This was actually one of Ed's strengths. Ed can edit a file that is basically anything that can fit onto the disk. And it does this by loading pieces of it into memory, working on those pieces, and then flushing those bits and pieces back out to disk as needed. If we take a look, we can see the Figforth assembly code here. And it's the whole damn thing. I chose Figforth here as a good example because it's a large piece of software. It's a good exercise for exercising the disk system for FujiNet. It's a good exercise for exercising the printer output for FujiNet because a listing of this is approximately 80 pages long. It's just a good workout overall. So let's edit this. We know, for example, that we need to take and make the change. Now, as part of the assembly process, I generated a listing using FujiNet's printer output, and I have it right here, right next to me. And I have taken a pen. I apologize, I don't have a camera so you guys can see this. But I've taken a pen and I've marked up the listing in red ink, indicating the changes that I need to make and where I need to make them, specifically the line number that I need to make them and where I need to go. How do we take and translate those changes into commands for ed and therefore the changes that we need to make to the file? Well, let's take a look. First, we need to open the file. You'll notice that ed opens the file and it returns immediately because, again, it hasn't loaded any part of the file into memory. Now, normally I would need to use something like the Z command or one of the line positioning commands to position into a chunk of the file. But I'm actually going to use another convenience function altogether, the N command. The N command will search for an occurrence of text throughout the entire file, paging it in and paging it out as needed, and stopping when the occurrence is found. We use the N command and we look for the string that we want to find. In this case, it is a label called cout, which is the console output command. And we want to search through to the end of the file. So we do this, we follow that up with a Control Z or Control Z. This will take a moment because it's actually taking and swapping out, it's actually swapping in and swapping out parts of the disk file here, looking for that occurrence. And when it finds it, it will take and stop and give me a line number right where the occurrence is found. And from that moment, I can take and make the necessary changes that I need to make. Or if it's not the right occurrence, I can repeat the command and it will continue onward from that point. We're going to wait here for just a moment for this to finish. And yes, I'm keeping these pauses in here so that you guys can get a good indication of what it was actually like. It took time and it took effort to have a computer take and sift through text, looking for occurrences of strings, particularly a large set of text like this one. We found an occurrence over on line 3454, and if we take a look, we can see we're kind of in the right place. We can kind of take a look, for example, and we'll see that this is cout, which is the, if we actually take a look just a little bit before this, this is actually the start of the CP/M console and printer interface. And these are equates that map to CP/M BIOS calls. So we're in kind of the right area, but we're not quite there yet. Let's do it again. Oops, sorry, try that one more time. And now we'll see that we're at line 3475, which if I look on my notes, that is exactly where we need to be. And if we take a look, we will see if we type the line, that is console output. Okay. Great. We are right where we need to be. So let's go ahead and start adding the bits and pieces of code that we know that we need. Bam. Okay. At this point right here, you'll notice that it said push right here. And if the one thing that's not immediately evident is that the cursor is not at the start of the line. It's actually just past the label C out. But I digress. That's fine. So we need to use the accumulator to we need to use the accumulator to do an and, a logical and of every character that we're going to send out to the console to mask off the topmost 8-bit. So we need to go ahead and do that. We need to take and move the character, which is currently sitting in the C register, to A. We need to then take and do an immediate and of what's in the accumulator to strip off the topmost bit. And we do this by saying that we want to AND this with 7F. 7F is essentially the bottom 7 bits set and the topmost bit set to 0. And for the sake of consistency, I'm putting my comments in caps as well as my changes for instructions. We then take the result here and move it back from C to A. And then we go ahead and restore A. We have to do this because the register is important to Forth for a variety of reasons, and we have to make sure that we preserve it. If we use any sort of registers for quick temporary processing, we need to take and remember to push things onto the stack, do what we need to do, and then take what we have off the stack so that everything is still nice and clean so that the rest of the program can run as intended. That's all we really need to do right there. We can finish the edit right here by hitting Control Z, Control Z, and if we take a look, and we do a little print here, we can see our adjusted routine so that we can give it a once over to make sure that it's okay. It looks good to me. So let's go ahead and finish the edit. And you'll see right here that add will do everything it needs to do to take that block that's in memory and put it right back into the file. Of course, ed tries to be as safe as it possibly can. It uses temporary files wherever it can so we don't accidentally take and clobber the original file, on top of which it creates a backup file. So it's a good idea to have enough disk space. You need to be aware of how much disk space you have. Finally, we have Bigforth and we have our backup file. In case this particular change didn't work, we can revert it. So now we can assemble it. We use Mac to assemble the result. We need to take and specify that the assembly is on drive A. We want the hex file to also be on A. I'm not going to take and produce a new listing for this one because I know it's okay, and this will speed up assembly quite a bit. And within about 5 minutes, we will have our completed hex dump here that we can take and load with the load command. What I've just done here is just one example of a particular change that a software engineer would need to make to a particular piece of software. It's how we did software engineering back in the old days. It was done entirely with a line editor, and it was done, most importantly, with a copy of a printout of the listing in hand. It was possible to use a line editor at this point because it was expected that you would scribble the notes for the changes that you were going to make on your listing and then figure out what editor commands you needed to do in order to accomplish those changes to write them back out. Now, I will not deny that full screen editors were a major improvement, major advancement. But line by line editors weren't bad either. They were extremely efficient once you understood the command structure and planned out what you were going to do beforehand before you did it. As an aside here, if I were to have generated a listing file, the assembly time would have ballooned from something like 3.5 to 4 minutes to closer to 25 to 30 minutes, especially if I'm sending that listing to the printer. So while it is important to have a listing file, it can be very helpful when you're doing quick changes, quick being a very relative term, to basically skip the listing and the symbol table output. So now we have our assemble section, we have a length, and we have a use factor, which is basically the number of symbols used in the symbol table. Mac has a limit of 255 symbols max, so FF, and so we're only using 31 symbols, which is quite nice actually. So with that, we have our hex file, but it's not complete yet. The fig fourth com that we have here is from the previous load. So we have to take and use load to take the hex file and turn it into a com file by loading it into memory and then using CPM's and then basically just writing out the resulting records. This is much faster than the assemble. Of course, being a relative term. So we have here our fig fourth com. It starts at 0100. The last address there, number of bytes total. So we're just under, looks like we're just under 8K. Here, yeah, okay. Groovy. So, 8K total memory usage here. So, okay, we're good. Let's take that and run the result. Yay, okay. Text still looks okay. Whew. And let's do a little test here. Oop. I need to change the backspace character, but that's okay. And there we can see our vocabulary list. And now you can see the greater than and less than symbols are now being properly interpreted. And you're not seeing bits of You're not seeing bits of Atom logo. This is important because those symbols are actually fourth words, the things like greater than, less than, etc. Those are all valid fourth words. And we can see that this works. We'll go ahead and create a quick little oops. Let me scratch that. Try that one more time. Hello worked. Ah, that works. And yay. Okay. So that works. We're good. And I'm going to end the video here and try to plan out the next steps so that we can start the bootstrap process of moving this over as a complete EOS application that boots, self-hosted, works as intended. And in the process, get the editor and the assembler words pushed into the fourth environment here. So with that, I'm leaving it here. Hope you guys enjoyed this, and as always, have fun.